let's have a look at this little diagram, and I'll ask you to think this is a physical diagram of the internals of the pump. We've got our pump flange here at A. We've got the eye of the impeller at B. We've got the leading edge of the impeller vane at C. And at some point D through the impeller is where we're adding pressure back, adding energy back to the fluid. We're going to now look at the pressure that we're generating. And this is the suction pressure at point A. As we go through this area, will be a small friction loss. Okay? So this is our small friction loss. When we hit the leading edge of the vane, we're going to get a shock loading. And at that shock loading, we're trying to change the direction of the fluid. So we're basically hitting it with a guillotine. And we're chopping it up and pushing it in a different direction. Okay? That shock loading causes a pressure drop. So our lowest pressure drop is at point C, which is the leading edge of the vane. And if you remember in an earlier slide, the first appearance of damage was that leading edge. Okay? As we go through the pump, we start to add pressure again. And that means we get to a point somewhere here where it changes back from a gas to a liquid, and then it moves smoothly. So that's why we see these two distinct areas of damage. The first one is at the leading edge of the impeller vane, and the second one is halfway through the vane where the gas changes back to a liquid. So it's a double phenomenon. It's not a single phenomenon. And that's why it's so noisy, because in that particular zone, between the leading edge of the vane here and the point where it turns back to a liquid, is very violent. Lots of expansion, and it's in an enclosed space, so it becomes very noisy and lots of vibration is generated. That vibration goes back through the shaft, goes back through the seal, goes back through the bearings, all of which are connected. So that's where you get the mechanical damage from the phenomenon of cavitation. This is a little bit more of an easy diagram to understand. Here is our loss in the pipe. That short section, that's a friction loss between the flange and the eye of the impeller. Here's our shock loss, and here's our increase in pressure due to adding energy from the vanes of the shaft. The idea is the velocity should be going straight into the eye of the impeller, and that will be related to the match-up between the pipe diameter and the flange. And do you remember when we talked about installation, we tried to match the diameter of the incoming pipe to the flange of the pump, and the eye of the impeller is usually about the same diameter as the diameter of the flange, internal diameter of the flange. So velocity is not really an issue in that case. It's a question of energy loss. So there's no kinetic energy loss between the suction flange and the eye of the impeller. What you're getting is a friction loss, which is the friction of the fluid passing through that short section of pipe between the flange and the eye of the impeller. In the pipe, yes, I can understand that. But in terms of the flange of the pump, generally speaking, the eye of the impeller will be sized to match the diameter of the internal section of the flange. So when you look at a pump flange, you've got an outer diameter and an inner diameter. And that inner diameter, when you look through, generally matches up with the eye of the impeller.